And we are on the second session today with Stefan that will talk about Roslyn source generators, a super hot topic. I'm super interested in this technology, so I'm happy that you will talk about it. I hope you will find it interesting. As I will be posting on the chat, there is Discord when you can start discussions. And if you have any questions also, you can ask on chat here on YouTube. I will look, and if we will have time, we will ask at the end. So good luck. I'm listening. All you are listening. So I'm hiding myself, and the scene is yours. Thank you, Stefan.
Thank you very much, Konrad. I am absolutely thrilled to be here at the Dotnetos Conference, and I'll be talking about Roslyn source generators. Never send a human to do a machine's job, to quote a famous villain of one of my most favorite movies. This will be the Dotnetos Performance Edition of this session. So we're focusing about not only the performance of generated code, but also the code that is generating that code. So my name is Stefan Pölz. I am coding since a couple of years. I am now in the .NET space for roughly 10 years. I'm doing Roslyn for roughly 3 years, and currently I am a senior developer at Trayport in the office in Vienna. There is offices all over the place. Trayport is the primary network and platform for the European wholesale energy market. And there is actually a very good chance that the equipment that I'm running here to give this presentation is powered by electricity, which was traded over our platform. Anyway, this talk will be entirely my own. And I also list some of my alter egos here. And at the end, everything you see is or will be at GitHub. So I will provide you with the link at the end. And yeah, let's get to it. So, brief introduction, what is Roslyn? It's the .NET compiler platform. Those are the compilers for both the C# and the Visual Basic language. Now, as a consumer, me as a developer, I can also additionally use Roslyn to build plugins, components for it. For example, analyzers or code fixes in order to Alt-Enter or Control Dot and fix an issue, a warning, for example. But we will be focusing today on the generator side. There is 2 interfaces that we can implement, the ISourceGenerator and the Incremental Generator, and we will figure out all the intricacies along the way. To start with, I want to give a brief overlook of the laws of source generation. So a source generator gets as an input the code that the user has written. So if I am in a project and this project is also consuming a source generator, now this source generator is running every time we compile, actually every time we type something, gets this as an input and may then produce additional output. So we get the syntax trees, which is the codified representation of the C# text. And there is also the semantic model, which gives meaning to this text. We will have a look at this just in a moment. And then a generator can add additional sources. It can add 0 or technically an infinite amount. And it's just a string that we add to the compilation. But the thing is, it's only additive. We cannot remove, we cannot change code that the user has written. We can only add new sources. A generator, since it's technically an analyzer, could also produce diagnostics. For example, to give the user a warning if they are doing something wrong or not according to the patterns that this generator is enforcing. And a generator can also analyze additional texts. So not every document that we have in a project must be C# or Visual Basic. It could also be a text file or a JSON file as an additional text that we could analyze. The thing is about generator, they are unordered. So one generator cannot depend on the other generator. They all get the same input, so there is no order on generation. And two of the most prominent use cases is if we want to create special case code to avoid reflection in order to improve performance, or to avoid tedious boilerplate code that is adhering to some patterns, and the source generator can do it automatically. We will applying both today. So let's jump into the solution. I want to present you with a bit of a problem that we have here. So I'm having a struct which has two properties, which then basically get compiled to two fields. And now I would like to put this struct into a hash set. What we see, we do not overload or implement the IE-quotable interface or overload any get hash code methods. However, now every struct, we have a unit test here, this one passes, every struct is actually deriving from value type. And if we have a look at this value type implementation, we see it actually overrides. So in return, value type derives from object, because everything derives from object. And this value type now actually overrides equality. However, we see there is a check that can compare bits. Now, if this check is true, we will actually get a very fast version of this. But if this check is false, then we get a slow version. So we have reflection. This actually will be allocating, and it's not the fastest solution than a special case manual implementation. So the default could potentially cause problems. Same with the get hash code implementation. So for example, the get hash code implementation, the BCL team or the current implementation decided to only compare the first non-static field. Only the first non-static field is used in order to generate a hash code. Now, if we have more than one field, and if we now have several instances and they collide on this first field, we will have a lot of hash code collisions, and then additionally in a hash set, now this will be very, very slow. So one problem that we actually see here is we have here this struct. We initialize it first, both with the number is 1. This is the first field, and the second field, the string, with a different string. However, if we get the hash code, we would actually expect it to be not equal. But this test is failing. They are actually equal because only the first field value is taken into consideration by the default get hash code implementation from the value type. And this will then, in return, cause hash collisions. If there is a hash collision, now equality is invoked. So if I was to override the equals method and I throw a not implemented exception. Now if I run the test, where we are adding two values again, they are equal in the first field, but differ in the second field, to a hash set. And now this test fails. We actually get the not implemented exception is thrown because, again, we will have a hash code collision here, and then equality is invoked. So this will be not only, if this highlights that having hash code collisions can be very, very expensive. Additionally, since this is object, we also have from this struct type, this value type boxing. So we will have allocations, and it's not the fastest. So this is where the general guideline comes from to always implement equality on value types. Now let's have a brief look at a benchmark. While I'm explaining the code, let me run the benchmark in behind .NET 1-c release. We're using benchmark.net. And oops, this is actually the wrong one, sorry. Yep, that's the right one. .NET 1-c release. And in this benchmark, again, we have the same struct where we have the first field is an integer, the second field is a reference type, because also if a struct has a reference type, what we saw, this can compare bits in order to enable faster version of the equality cannot be used. So we will have the reflection-based implementation. And also the get hash code will cause collisions here. And we have a second struct, which is structurally the same. It's also a number and a text, but we're using the C#10 record struct. And a record struct actually creates a lot of code for us. Let's have a look at what this does. I'm jumping to sharplab.io. And on the left side, I put in this struct. And on the right side, we see a lot of code being generated. For example, this struct is now actually implementing iQuotable. And we're getting operators overloaded, and we get a hash code implementation equals, and so on and so forth. And if we now compare those, so I create a hash set for both the struct and the record struct, and add an item to both, and then an item where it clashes on the first field. And if we have now the implicit version and the explicit version, so with implicit I mean it's the base value type implementation, and with explicit that's the record struct. If you have a look at the performance, we see that the implementation of the value type where we don't overload the default get hash code and default equals is significantly slower than the record struct, which actually implements those methods explicitly. Or, well, the compiler does that for us. And also we have allocation. And in this example, I'm only adding 2 values in this hash set. So if there is more values, there will be more collisions, there will be even more allocation. So this could actually cause severe performance problems in our code. Now, a fix, I gave the fix actually away, just put the record keyword onto the struct, and the compiler implements all this for you. Now, when I developed this talk, this was with C#9, there was only a record class, no record struct yet. So the rest of this talk is assuming that the record struct does not exist. And we can leverage source generators to basically do the same, not exactly the same, but the very similar that the C#11 compiler with the record struct and read-only record struct feature is doing for us to implement equality and get hash code automatically. We could do it by ourselves, but it's very tedious. It's always the same pattern. And if it's a very repetitive pattern, this is a perfect use case for source generators. So let's write ourselves a source generator. I will start with a unit test. I actually have that prepared already. I'll just briefly browse through it. So this will be our reference. What I'm using here in order to unit test this generator is a package from Microsoft. It's the Microsoft code analysis. That's actually Roslyn package here. The Microsoft code analysis C# source generators testing package, and there is 3 variants, both for, all for XUnit, MS Test, and NUnit. So you can choose your favorite. And what we see now in this test, we actually have some code. This is the user code. So the user is writing, for example, a class. In that case, our source generator should not trigger. It should only trigger on structs. Now there is such a struct, but it should also not trigger there because a source generator adds new code, which is in a different not necessarily physical file, but it's in a different document. So we at least need to make this type partial in order to extend it. I also don't want the source generator to trigger if it already implements IQuotable. And if this is a record struct or a read-only record struct, the source generator should not trigger either. And this is what I verify. I put in the code and I assume no diagnostics. So nothing should happen. In that case, the source generator should have no side effect. However, if we actually have a candidate, in this case, we have here a struct, a partial struct, which does not implement iQuality yet. Now the source generator should trigger. And also I have another struct which is outside of a namespace. This is very important to keep in mind. We will see this. And now I have the expected code. And what we will see is also some best practices here. It's always good to add to the generated code an auto-generator comment so that tooling such as an analyzer knows, okay, this is generated code. Perhaps I shouldn't create diagnostics for that because the user has no, the consumer of the generator has no direct influence of what the generator is generating. I assume we are on C# 8 or higher, so let's enable nullable. And here is now the partial struct that the generator should create. And it's always good to refer to types to the global namespace, because technically it could be that a user in their namespace tests, also implements a system or an IEquotable, or has somewhere in the compilation a system.IEquotable. It's bad practice because it's causing name clash, but then the generator may fail or creating compiler errors because it doesn't really know which type. So it's always good. A good practice to refer to the global namespace. And also for generated type, so not the entire type is generated, just methods on it. So it's also nice to put the generated code attribute to it so that non-source code based diagnostic tools also understand, okay, this is a generated code. The user has not written this. And then we generate, just as the record, the C#10 record struct would do for us, we want to generate the quality operators. We want to generate a hash code implementation, which uses both properties. We implement the equals, where we check, is it this type, then cast it to the special case. And also the generic implementation from the interface. Then I have the same thing again for the other struct, and then I just verify that this code is actually created. And here we can also pass a bit of it's a hint name, so that tooling knows it's not necessarily a physical file that the generator is creating, but to give tooling a bit of a hint of how to name it and make it more approachable. All right, now let's jump to the generator, because we now have a failing test. Actually see down there, this generator, we expect something to be generated, but there is nothing generated, so it's time to fill the gap. Now, generator must be targeting .NET Standard 2.0. I do multi-targeting with the latest .NET framework in order to have the latest nullable annotations from the BCL. However, the generator itself must be .NET Standard 2.0. We see that actually down here, it must be standard 2.0, because the generator could be consumed by Visual Studio. That's still based on .NET Framework, or on other tooling which maybe hire something which implements .NET Standard 2.0. And the most important package that we consume is the Microsoft Code Analysis C# package. I also use workspaces for a bit more features. This is where the interface lives in that we now will implement. So here is the basic stub of our source generator. We have here our value type equality generator. It implements ISourceGenerator, and we get those two methods. We get the initialize method and the execute method. I haven't implemented them just yet. It's always good to, well, actually we must put the generator attribute on top of that. Otherwise, tooling wouldn't know how to pick it up. And we can give a hint for what language this generator is generating. You could also have a generator which creates Visual Basic code. And now we have in the initialization phase, we can register a so-called syntax receiver. And this syntax receiver is again another type. We have here the isyntax context receiver. I have here static factory method. Basically here we have the onVisit syntax node, which gets called, as the name says, on each and every syntax node. So what's a syntax node? Let me jump to the test. Let me grab some of the code here. And once more, put that into SharpLab, putting out of the left side. And what you can do in SharpLab, not only display the compiled and decompiled C# code, or the lowered C# code in that respective, we can also have a look at the syntax tree. And this is how the code looks like from a Roslyn perspective. And we see this is a tree of nodes. So we have a namespace declaration. Within this namespace declaration, we have a struct declaration. Now what we see here, those are tokens, like the public keyword, the partial keyword, the struct keyword. Those are tokens. Those are the terminal nodes in our tree. So they have no children anymore. Then we have two property declarations. And the property declarations, again, they have a public keyword, which will be a modifier. They have a type, in this case, a predefined type, because it's a language type, int, and the int keyword. We could also have system.int32 here. And then we say this is no longer the predefined type, it's now a qualified name. And what we see here, this is just a name, system.int32, from a syntactic point of view. It doesn't really have meaning that it's actually the int type that most APIs use. For that, we need the semantic model. Now, since the generator is actually getting each and every node that we see here as an input, we should filter types or nodes that the generator is interested in rather early. So I will be copying the implementation in order to speed things up a bit, and so you don't have to see me write some typos. We first check, hey, is this node of type struct declaration? If it is, we also check if this node has any modifier of kind partial keyword. So we want all the structs which are partial. We don't get the records here, even though if it's a record struct, because a record struct would be a record declaration syntax. And the record declaration syntax, again, has a node, which is the class or struct keyword node. So we know if it is a class struct or a record struct. So we already have the correct types. But now we only have the syntactic thing. We actually want the semantic thing, and that we get via the semantic model. So we can actually now get the symbol of this type, and this is now actually basically a meaning. And from this symbol, we can check if it implements a specific interface. We could check if the user has basically syntactically written system.equatable, but again, it may be a different system equatable. It's just text. We want the meaning behind it. And so we ask the semantic model. It has a compilation, and we get the system equatable interface. And this is actually the interface that we want to implement. And now we check on this type. Does this type already implement? So is any of the interfaces that this type implements this equatable interface? And if it isn't, now this is a candidate. So this is a struct that is partial and is not implementing the equatable interface just yet. So we put it into our candidates list. And then we come to the execution phase of the generator. I will now copy quite a bit of code in here. So first we check, do we actually have the syntax receiver? And then we iterate through each and every of the candidates, get those symbols. Here I now get myself all the properties. So we're getting the members, all members which are of kind property. We could also do field. Actually, we should use field here, but it's the code that we generate. It's a bit more easier to use a property here. But if you write this yourself, you should use the backing field. And now we generate code. We see this is just a string. That's it. And we, as we wanted, first have the auto-generated comment on top of each file and the nullable enable preprocessor directive. And now we have here a bit of code. We need to check if this type is in the global namespace. Because if it is in the global namespace, then we shouldn't print the namespace here because it's actually in angle brackets global, I believe. So this would not compile. So always check if it's in the global namespace. And if it isn't, then we can emit the namespace, the containing namespace of the struct. Now we create our partial struct declaration. We implement the IA quotable and now generate the string. You can generate the string however you want. You could use a string builder. There is also other template-based models that you could use, but bear in mind it should be fast because the generator will be running a lot. And basically, we just implement all those where we fill the gaps with the real struct name. For the implementation, actually do a bit of a string join. This is just to make this example a little bit easier. You shouldn't because string join. Yeah, so we have some, we have a link here and also string join allocates several strings. It's not the best. String builder would be easier, faster, but the code wouldn't be as nice. And the equals and so on and so forth. And for the equality method, we use the equality comparer. And then when we have assembled the string that we want to put into the compilation, we then give it a name. We see here that's the hint name. Tooling will be using this. We will see this in just a second. And we say the name of the struct dot value type equality. And it's always good practice to end in a .g.cs. Again, to indicate that this is generated. We could also write .generated. It's either .g.cs or .generated.cs. That's the pattern. And I believe I have a compiler error somewhere. Should be fixed. Now let's see if our unit tests are passing. And they are wonderful. So let's jump now into the unit test that was previously failing. That's the wrong unit test. Sorry, we got that one here. Because this one is actually using, also calling into, so because here we have here a hash code collision with the default implementation. So this test is still failing if I run it. We see it here. But now let's actually trigger the generator because the generator is waiting for a struct which is partial. So let's add the partial keyword to it. And let me run the test again. And now it turned green. So we no longer have the collision because what we see, we can go to the Explorer, jump to the consuming project in the dependencies tab, and have now here, so in the dependencies tab, we see here source generators. And here we can look at the file that the generator is creating. This is very similar in Visual Studio. If we double click that, we see here, this is now the generated file, or not necessarily a file. There is a compiler flag you can set in order to also put it on disk so you can view it, but by default it's in memory. And here it is. It's the mystruct value type equality.g.cs. This is the hint name that we have indicated. And here is the generated source code. And this is just a string that we put here, and then the compiler now compiles it again together with the rest of the user code, and this will now be the final compilation. So let's go ahead and run this benchmark again. But I should change the source code first. So also make now this struct partial, so that again the source generator can pick it up and create the partial struct declaration with the additional members. While this is running, I want to highlight one potential issue of generators. So if I jump to the implementation of the generator, and perhaps let's add a comment. Let's say datetime dot UTC now. Let me recompile. And if we now jump to the example here, where we'll now make the struct read-only in order to, not read-only, partial. So the generator can pick it up. So we now have the generator here. We can have a look at the code. And if I put this next to the user code, and if we have a close look here at the time, we will see I will change the source code, and now the time is updated. I just hit enter. That's it. And now the time is updated. So every time we edit our source code, the generator will run, which means the entire source tree. Now, if this is a huge project, it will be a lot of syntax nodes that, again, we need to parse and then generate the source code anew. So we always generate this entire string again. And this may be a problem if this is a huge solution. Actually, Microsoft experienced this in the runtime solution when they started introducing generators in .NET 6. And this is a bit of a flaw of the ISourceGenerator programming model. We will fix this just in a minute. But the problem basically highlights, although I do not change the struct that I actually create source code from, but some other code, I generate everything again. This is a bit of an issue of this programming model. But going back, now having a look at the benchmark, now both the implicit and the explicit. So the explicit is the record, the read-only record struct, and the implicit is the now partial source generated version. Now they are pretty much the same. There is no allocation, so we eliminated all reflection, all boxing. We no longer have any hash code collisions, or at least we have reduced the chance of hash code collisions significantly. And now this type is ready to be used in hash sets. So we now made the code fast, but what about the generator? Now, I said that the programming model of the ISourceGenerator is flawed. So there is a different programming model. Now, ISourceGenerator has been added in .NET 5, which is in the Roslyn world. That was the package version Roslyn 3.8. I'm using a feature here which was introduced in Roslyn 3.9. So, but this is the .NET 5 world of source generators. Now, since .NET 5 is out of date, it's safe to update to the latest version of source generators, which is the incremental generator. Now, this has been added in .NET 6. In Roslyn Lang, this is version 4.0.1 and higher. And we will actually see this if I have a look at the type, at the CS proj. We see here the version of the code analysis C# package 4.0.1. So this generator is now compatible with .NET 6 and higher. I couldn't consume this in .NET 5 or lower. Now let's enable this generator. Actually, before the other generator, I will comment this out so that we don't have two generators struggling for implementation. And what we see now for the incremental generator, this only has an initialize method. The execute method is gone. There is only the initialize. And in this initialize, now this newer programming model is bound to set up a pipeline. So we will be setting up a pipeline of several steps. And the benefit is that within this pipeline, if a previous step creates the same thing that was generated in a previous compilation, so before we hit enter, then subsequent steps will be skipped, and the same, so what was generated will be cached and then will be reused if nothing is changing. And this is why the incremental generator model is significantly better for big solutions, because this example that we had before, if I change some code which is actually not relevant to the output, then some part of the pipeline can be skipped, and this is how we win performance. So now let's come to this initialize method. We will set up the pipeline first. I will grab some code to make it compile. There we are. And so this context that we have has several so-called incremental value providers. So we have, for example, the compilation as incremental value provider. This is very similar to link. So we're setting up a bit of a pipeline where we then later, when this link query, or in this case, this incremental generator pipeline is executed, then all the values get filled. So it's deferred execution, and the pipeline, this link, this somewhat of a link statement, it's not link, but similar, can be reused. And we start with a syntax provider. So this is now the equivalent to the syntax receiver that we've seen. And the syntax provider has two steps. It has a syntactic predicate, which checks whether this node is interesting or not, and a semantic transform, which is actually, the name already says, syntactic is only the nodes, semantic, also the meaning, so the symbols. So let's bring in some code. And functionality-wise, it is the very same that we wrote before. We will see very similar pattern. So for the syntactic check, I just do something very quick. The syntactic check should be super, super, super quick, because this would filter out the most not interesting parts already. So I'm searching for all the struct declarations which have the partial keyword and return true. Now for every node where this predicate is true, we will go into the semantic transform down here, where we now have, since it's the semantic, we also now have the semantic model. We don't have it up here. This should be super, super fast. This should also be fast, but we can use the semantic model. And I do basically the same check that we did in the syntax receiver. So the syntax receiver is now split into two parts, where we again get the type and we check if it implements iQuotable, and if it does not, we return that type. So we see we don't store this in some list, we return it like in link, like a link selection. Otherwise, we return null. This is why I filter the nulls out of there. So now we have all the types, the named types actually, so which is a type, which has a name, of the structs that are partial and do not implement iQuotable already. And now we must register, since there is no real execution phase anymore, we basically register a callback. So we say register source output, and we pass in this incremental value provider. Now this pipeline could be way longer. We could combine it with, for example, the compilation, what we saw, or other parts of this context, or we could also filter here. So it's link-like. There is like a combine. With the combine, we can combine incremental value providers. We could also select a transform or where filter. It looks similar to link, but it isn't. If we have a look, this is actually a separate type. This is not in the system link namespace. And then we have our callback. And this again will look quite similar to the execution phase of the previous generator, where we again filter all the properties, and this is the very same code we create the source code again. And at the end, we add the source. Where now the difference is that we filter out some nodes prematurely already, and if nothing is changing, so if we don't modify any structs, and then those types are equal in previous runs, then this execute method won't be run again, because the generator sees, okay, previously with the same filtered input, I created this output and can then reuse it. And in huge solutions, this will be a big performance gain. And let's actually test this if it's also working. Let's have a look. I will rebuild and have a look at this example. Check the generated source code. We now see here in the name that this is no longer the source generator, but the incremental value type generator. So it's actually the new type, not generating basically the very same code. But if we would try this generator in a huge solution, we would already see a difference in the speed of generating this source code. And this is one more thing I would like to show is we can also benchmark our source generators or our incremental generators. There's actually a small library that I wrote. I called it it will also be in the slides if you're interested, the F0 code analysis C# incremental generator.benchmarking. And with that, we can write a benchmark for the generator, where this is a pattern that I'd like to use in the setup. We create the code that is the input for the generator, and then the benchmark itself invokes the generator. And also I do some cleanup, which is basically a test. So the benchmark would fail if it isn't creating what I actually intend to. And this is how source generators can not only create code that is faster, but also with the incremental generator model, we can create a fast generator itself. So for the end, I want to highlight some best practices when using or when generating code. So always have the auto-generated so that analyzers know, okay, this is generated code. If you're sure that the user is on C#8 or higher, make it nullable. Always use the global identifier in order to avoid potential name collisions. Put the generated code attribute on the parts. Have .g or .generated.cs in the name so the tooling knows, and minds the required .NET version. So if you're using the 3.8 ISourceGenerator, the minimum version is .NET 5. If you're using the later 4.0 incremental generators, the latest version is .NET 6, and so on. So if you're using later Roslyn versions, the user's SDK also must be upgraded accordingly. Also keep in mind the language version. Since we are only generating a string, we could be generating a C#11 string, but maybe the consumer's project is still on C#10 or even lower. So keep that in mind. Performance is crucial for the generator because it may, in an IDE, in Visual Studio, in Rider, it runs a lot. So it should be very fast code. It's very important that the generator is deterministic, especially for the incremental generator, because otherwise this pipeline with the memorization, the caching, wouldn't work correctly. Always have testing or unit test, integration tests. And there is, I suggest to use the analyzers which are included in the .NET 5 SDK and higher by enabling analysis mode to all, and also consume this package, the Microsoft Code Analysis.Analyzer package, which is a meta analyzer which analyzes the code, the source generator that we built. For example, I would get a warning if I would, okay, not sure why I get the warning, but I should get a warning here when I don't have the generator attribute here, because tooling wouldn't pick it up and it wouldn't just work. It just wouldn't work. Yeah, and I always like to give the hint. In release modes, treat warnings as errors. This may solve some issues. And yeah, so I have here the link for the repository where all the source code of this presentation and also some more resources that you perhaps may be interested in, you can find. Perhaps we can put this into the chat so that you can just click it. And if you would like to connect, I'm on Twitter. I am almost every week streaming on Twitch and YouTube. And I also linked here my GitHub and NuGet links if you want to know more. And there is only one thing left to say. May Roslyn be with you.
Awesome, thank you very much. Source generators are mind-blowing. Especially they were complex at the beginning and they decided to add incremental ones.
Yeah, so it's even tougher now.
Yeah,
the programming model of Roslyn in general is, it took me some time to get used to, but once you have the hang of Roslyn with the syntactic tree and the semantic model, and then later on understand the pipeline-y approach of incremental generators, I find it really fun to build build code that builds code.
I would suggest writing a book about it.
Ooh.
Or a course or something like that.
Are you nerd sniping me now? Okay.
Yep. No pressure at all. Okay, thank you very much, because we are running out of time slowly. So thank you, Stefan, for this awesome talk. It will be recorded, available afterwards. I will be watching it probably once more because of all this stuff there. And if you have any more questions, go to the Discord, because we need to end this one. And I have even some, but I will ask there, just not to prolong it now. So thanks again for being with us. Thank you for everyone listening to us, watching you, and see you in the next session. And see you on some conference in Prague, as far as I remember.
Ooh,
right?
Yes.
If everything works out, so fingers crossed.
And knock on wood.
Exactly. Thank you, and have a nice evening then.
Thanks for having me. Goodbye.